Good morning. Today we can say the resonance response for undamped and undamped single degree of freedom system subject to harmonic load force. We can remember the dynamic magnification factor D is given from equation 13. This equation you is given in the precedent video. So is 13 is here, okay. D equal 1 divided for rising 1 less beta elevated 2 all elevated 2 plus 2 for C for beta all elevated 2. So the D we can simplify with C equal 0 over rapport 1 divided 1 less beta elevated 2. Resonance occurs when the frequency of the applied load match with the natural frequency, so beta is equal 1, so 1 less 1, this rapport go in the infinitive, so D is equal infinitive and have the resonance. For undamped system we can rewrite the same equation 13 is equal is there, and correspondence of resonance, so per B equal 1, this equation, so for undamped system D max is equal to 1 divided for 2 for C. So this is the two equation in the two case, for undamped system and for undamped damped system. Using differential calculus in this equation respect AB and equate the differential equation to 0, the magnification factor so give the frequency ratio beta max equal 1 racine 1 less 2 for C elevated 2, so the D max become this equation. For a reasonable amount of damping, the difference between this of equation 16 and 17 is negligible. You can remember now we can plot we can remember the value of déplacement is given from this equation, and now we want to calculate the coefficient IB, the constant in this equation. The system is assumed to start from a completed state of rest, so its mean for t equals 0 is the déplacement is equal 0 and the velocity is equal 0. And obtain the constant A is equal to this value. We can simplify this formula with the standard engineering assumption, so with the low damping, so the system is in resonance, beta is equal 1, the forcing frequency equal natural frequency, so omega bar is equal omega. If the damping ratio is small, the square Xc elevated 2 is negligible, therefore the damping natural frequency is roughly equal to undamped natural frequency, so omega is circa equal of omega d, and this term in sin omega t become too small to, and we can ignore it in the formula. So the displacement of equation we can simplify in this way. Divide for the static displacement P0 slash K, we can obtain the dynamic magnification factor dt in function of time, and give the 20 equation. If damping ratio, so Xc equals 0, this equation become indeterminate. Applying the differential calculus, so using the rule, Hopital rule, we can resolve this indeterminate limit, so obtain the equation 2021. We can plot now this equation using Python code to visualize the graph of magnificent factor, and obtain and can you can obtain the graph. We can see specifically uh, the line of this program, this Python code. There is the line 89 with import the library NumPy for mathematical operation, array generation, and import library for creating the visualization. After define the beta for the steady state plot and the timing between 0 and 60 seconds, and define the natural frequency set equal 1 radian for normalized simulation, and define the damping ratio for comparison. So there is a C small equal of 5% of damping, large small for 15 damping, C medial for 17 damping, for critical 100 damping if the critical damping. After define the function the steady state and calculate the magnificent value, and after we can calculate the value for the undamped value. So here we can remember there is the graph go to infinitive because there is the resonance. So the line 15 is right to prevent the code to crashing to division by 0, and the line 14 replace point extremely close to beta equal 1. So this trick Matplotlib leaving a gap to verify asymptotic rather than drawing and ugly the connecting positive and negative infinitive. And after calculate the equation for undamped solution, in the dampened time domain resonance response in the 14 case here, and the plot all in two graphs. These two graphs we can see here. Okay, there is a first graph and second graph. And first graph there is in the x the ratio beta is the rapport of omega divided for omega bar. There are the resonance in correspondence of ratio beta is equal 1, and you can see the red line for undamped system. So for C equal 0, there is the resonance, the curve go to infinitive. And after we can plot the damping system for different increase value of xi, so for xi equal 0.05 is the blue line. After for xi 0.15, the green, the orange for 0.7 for xi equal 1 for the violet graph. And in the right graph, there is the representation of a magnification factor in function of time, and so we can plot the dampened system for the different value of xi. And for the undamped system is the red line. You can see the value of magnification factor become increase to infinity in function of time. And calculate for the dampened case, we calculate also the value of d max, is the point line in blue, green, uh, and orange line. We can visualize this in with an in simulation. We can see for undamped system, so for xi equal 1 and beta is equal 1, this is the graph. We can see the frequency is omega, natural frequency is omega is equal 4.47 in the table. Natural frequency is the same. The initial displacement is equal to 0 and the velocity is equal to 0. For here for xi equal 1. For xi equal 0 set 0.7, the displacement become bigger, and for xi equal 0.5 increase this displacement. After for 0.5 we can see also increase this value more. Okay, it's all. Thank you. Bye.